Hey, how y'all doing? Hopefully well.
Yeah, good. How about you?
Well, I just realized my volume's too low for me to hear properly, so I turned you up. So that's good. Okay, so that's it for that part of the announcements. Hey, another announcement. It seems like this is week 5 of 5, so my gosh, we're like darn near at the end of this thing. And I have enjoyed it so far, but to be honest, it's a Zoom class, and so there's always that. But looking at your exam scores and how well you're doing, I'm really pleased that your understanding level is pretty darn good. So there's that. Yay. Okay, so maybe we'll start with administrative questions if there are any before we move forward. Okay, so to do I see a question in the chat. Yeah, so I'll adjust the Lab 12 due date. I apologize for that. I sort of borrowed that one from a past term, and that term, they turned in their labs at 10 a.m. right before the in-class portion. So yeah, I'll make that fix. And if I don't make that fix by, well, I don't know, later today, let's just say 6 o'clock. If you let me know, I'll make that. Uh, Hopefully, I've also set it so it's with your week 3 lab groups. Again, you remain in those same lab groups as before. The reason largely is none of you've said you have a preference for switching to a different lab group. So that makes me relatively happy because it means you're getting along. Okay, so any questions about other matters, administrative in nature? Okay,
What
how about,
dates are the
yeah, please.
finals open?
Okay, yeah, great question. Thanks, Claire. Let me talk about the final exam, okay, and in such a way that maybe it clears up some confusion. I had a good email over the weekend, and this is one other thing that I'm glad you mentioned it because I want to make sure everyone had heard the exact same thing, and that is in particular the final exam is cumulative, but in a way which allows me to break the exam into two separate chunks. Chunk one, I will call exam 3. Yeah, literally, it is stuff we've done since exam 2. Okay, so that will be like one half of the final exam, a same length test, 50-minute test, and I'll give you 55 minutes. Well, no, more than that because it's a final exam. Yeah, more time per question. So let's normally a final exam goes 3 hours minus 10 minutes, 170 minutes, half of that. So 170 over 5. My gosh, that's hard for me to do math in my head, but think an hour and a half, a little bit less, barely less than an hour and a half. And so plus an additional couple of minutes to scan, upload, turn things in. So think an hour and a half for just exam 3, the non-cumulative portion of the exam. And the cumulative addition to the exam will correspond to, well, material across the whole of the term, beginning to end, sort of like it's almost as though, well, we've tested you on every single individual bit. There are some things which could be tested best in terms of how they relate to maybe some earlier learned concept. So two separate parts of the exam. So there's exam 3, and that's going to be just stuff since exam 2. Then there's the cumulative addition portion, and that's material from across the entirety of the 5 weeks. And you should think, well, what was covered but not already emphasized? What was maybe something that came up, but because of the timing of things, maybe is like right before one of the midterm exams. And so because it was right beforehand and maybe didn't show up so much on the midterm exam. So were there things that were so important that we would need to have them on this new test? Okay, the cumulative addition. Or are there things that are so important that of course that even though we've already tested you on it, we would want to make sure that if you had a misunderstanding earlier, you have the chance to demonstrate you have a correct understanding today. Okay. So exam 3 and the cumulative addition, they will be two separate exams. Glad you asked the question, Will. Two separate exams, each of which is scheduled for just like an hour and a half. The time will be in there shortly beforehand. And you could take them at any point in time after we have finished up class on Thursday. Okay, so Thursday want to sort of have time to do review questions. So they'll both turn live as of 1 p.m. And you'll have until at least Friday midnight. I might choose to have it go until Saturday at some point in time, because that way you have the chance to sort of put your best foot forward, and across the group of you, as long as you're able to get it done on time, we're all happy. Okay. So yeah, two separate exams, and you don't need to do it all at once. And you don't even need to do exam 3 before the cumulative addition. You could do the cumulative addition before exam 3, and some students would even go so far as to study between the two. So in other words, if you say, well, I want to focus on just the recent material first, you could do exam 3 first, and then go back and take a couple hours and review all of the content from earlier. Or you could study up everything so far and sort of take the cumulative addition first. And if there's something that is in chapter, in the that will be likely test on exam 3, because it's a recent concept, and if you feel you didn't really get it, you know what to focus on to review, or maybe learn for the first time that material that is likely coming up on your exam 3. So the order just doesn't matter. It's as long as you get them both done in time. That's what does matter. Okay. Any other administrative questions? Okay. How about questions related to this chi-square method of looking at, well, okay, sort of in general, categorical response variables, or categorical hypothesis testing. There is a collection of categorical confidence intervals in the context of chi-square, but we're not really going down that path today. We only have so much time in this class, so that's okay. Any questions about chi-square as a test? How about the categorical binomial response confidence interval, the thing that I termed P tilde, which our authors do a great job of explaining the algebra of how we got to that P tilde, the add 2 successes and 2 failures, and then treat it as though you had an augmented sample of, n plus the extra 4. Any questions about that? Okay, so let's get into today's content. And today's content is about analysis of variance in chapter 9, sections 1 and 2. And then tomorrow will be the rest of 9 and a little tiny bit in chapter 10, where we're going to deal with experimental design. Okay. And then on Wednesday will be more on the topic of regression. More on the topic of regression, not more on regression. Okay, so yeah, learning more about regression. Last call for questions before I sort of share a screen of blank and start writing things down. Okay, I'm really glad I paused there. I almost hit the stop meeting button, which would have been the wrong button to press. Okay, so let me share a screen, and we'll see what we get into, what trouble we get into today. Okay, so what we've got here is, yeah, this blank screen, and okay, come on. Hold on. Okay, there we go. And not yellow, but let's go with black. In analysis of variance, it feels at first like a t-test that compares 2 separate means. What if we have, however, not just 2 groups that we'd like to compare the means of, but say 3 or more? In ANOVA, which is short for analysis of variance, okay? And literally it's a great name because we use an analysis of 2 variances to compare means. So yeah, it's not an analysis of means. There's a whole other procedure there that does something different. Analysis of variance is the way we compare 2 plus means. And so literally, if I guess I have only two groups, I could use the method that we're going to talk through today, but it's not quite as good as the method of the independent samples t-test that we prefer, the one that doesn't assume equality of spread across all the groups. Okay, so let's draw sort of a box diagram, and we're getting used to these things by now. And what we have here is K populations. There's population 1, population 2, population 3, and I guess I'm presuming K is at least 2 here, but I'm sorry, shoot, 4. What was that? Population K. Okay, so we've got K separate populations. I'm going to write this out as though we have K groups. And K might be as small as 2, but probably you wouldn't try this with a sample of 2, because again, you would use the regular t-test. And I'm going to presume we have what looks like a normal curve in each of these K populations. And I'm going to sort of quickly say, yeah, I'm showing you a normal population. That is one of the assumptions that we need to make to use this analysis of variance method according to our textbook. I do want to let you know that simulation studies from the last 25 or so years have shown that you maybe don't need normality as much as the book says you do when it wags its finger at you. Okay, so we've got these K populations. There's K separate means, mu1, mu2, all the way up through mu k. And there's a standard deviation that's presumed common across the K separate populations. Okay, so I'm writing sigma, not sigma 1, sigma 2, sigma 3. I'm just saying they all are presumed to have the exact same population standard deviation. And like I just said about the normality, recent simulation studies have shown that, well, in some cases, you don't actually need equal spread in the populations to use the procedure comfortably. Okay, so I'm going to tell you the party line, same standard deviation sigma and normality in all the groups. But if you talk to a professional statistician when you're working away on your problem, the statistician might say, well, you maybe don't need to be that extreme. Okay, so we've got our K separate populations, and our null hypothesis here is mu1 equals mu2 equals all the way up through mu k. They're all the same. If you will, no relationship between what group you're in and then the average response. On the other hand, well, at least one mean differs. And like last week on Thursday, the composite null hypotheses, lots of equalities in the null hypothesis. A logical negation of that means at least one of those equals isn't. Okay, and so that would say at least one of the means differs from the others. Okay, there's no great way to symbolically state an alternative hypothesis because I would list off a lot of possible cases, like mu1 equals mu3 equals mu4 equals mu5 up through mu k, but mu2 is different, or mu1 and mu2 are the same, and mu3 and 5 are the same, and mu4 and mu6 are different. I don't want to list off all of those possibilities. I'm just going to say at least one is different from the others. Okay, so in that context, what I like to do is open up a data set here and maybe, excuse me, open up a data set here and show you an example of the problem where we might have exactly something like this occurring. Okay, so opening up the data sets. And if you happen to have downloaded the data sets already for the course, and shoot, yeah, okay, there we go, courses. The Finder thing in Max, or whatever it is in the system that you prefer. It's great that you can now display so many different ways. I'm thinking sometimes I'll display alphabetically, or sometimes I'll display by reverse date order. Sometimes I'll display by date order. And then if I walk away and don't set it back to the former style, it can be frustrating. Okay. So you're dealing with a data set in the lab. So I have to be sure to pick that one, not that one, but the other one that is great for this example. Okay. I'm going to pick diet and lifespan and diet lifespan, DIET, diet and lifespan. Good. So these are data from a Stanford study from the mid 1980s. And it was performed by people who, a collection of people, researchers who thought maybe if we reduce the number of calories a critter gets, it will live longer. Okay, so there's a whole on diet craze. You've maybe met people who try this. At one point in time, there was this CRON, C-R-O-N, calorie restriction for optimum nutrition diet. And it was based in part on this study where they tried mice with a different collection of treatments or diets, and we then looked and see how long they live. Okay, so how long do you live? Actually, no, it's rats. How long do you live based on what we feed you? Okay, so the different diets here, I'm going to sort of list them out in sort of funny order. And P is no restrictions at all on your food. So N for normal. P, I forgot that what it stands for. Okay. N/N85, that is the second diet. And that's set to 85 calories per day per gram of body weight, something like that. And I'm not sure if that's calories, probably it's kilocalories per gram of body weight, but I could be wrong. If we made this comparison, which maybe I should choose a different color for, we're answering the question, does restricting your number of calories to the biologically optimal value for number of calories, literally is it going to be best to eat what you're supposed to eat according to biologists and animal scientists? Is restricting your number of calories to the biologically optimal number, is that better than letting you eat however much you want, which is the NP diet? Okay. There are some other diets. Another diet is N/R50. We reduce the number of calories to 50 calories per day instead of the 80, NR50. There's another one, NR40. So yeah, literally 40 calories per day. That's a lot less. Then there's RR50, where before weaning and after the rat is reduced in terms of the number of calories. Okay. And up front says before weaning, there's nothing. R up front means it's reduced. And then there's a low protein diet, so low protein. And so I guess these arrows here form natural questions, well, let's try this one for example. Is reducing the calories before you wean the rat going to impact the length of life? Or perhaps if we're dealing with that question and that arrow, is a reduction in calories to 40, which is like less than half of what the biologists say you should eat, is that different than reducing to only 50 in terms of the average length of life? Or, is a low protein diet going to be, it's the same diet in every way, except for the purine or rat chow is made with low protein content. Okay, is reduction in protein as well as calories very helpful? Okay. And so again, across these 1, 2, 3, 4, 5, 6 different diet groups, we have the opportunity to tackle this question. So K is 6, and we have data like I'm going to go with X bars or Y bars. I'll go with Y bars. Y bar for group 1, Y bar for group 2, Y bar for group 3, all the way through Y bar for group 6. I've got 6 separate sample means. And the null hypothesis is the population means are the same. And so if the null hypothesis that all the population means are the same, mu1 to all the way up through mu6, if that's true, I'm thinking the separate sample means should all be quite close to each other. You'd think the sample means should be close to each other if the null is true. If the sample means are not close to each other, then you might want to believe the alternative, that at least one of the groups has a different mean length of life than do the others. Do any of you have questions so far? Okay, let me do a quick screenshot and get that off. And let's do the analysis like that you're going to need to do in the lab today. Okay. So your explanatory variable is what treatment, and you can notice that this is categorical in nature, like a little red says nominal. Okay. And then the length of life is lifetime, and that's like this little blue triangle that corresponds to your friend quantitative variables. Under analyze fit y by x, we have the method we need. And just use English. Does the lifetime depend on what you eat? Does the lifetime depend on the treatment itself? And seems like I've got all my sort of data in the right place. I click OK. And we see some output that suggests maybe, literally the NP diet people, mice, rats, they tend to not live as long as the N/N85 rats. And these other 1, 2, 3, 4 diets seem to have a longer length of life than certainly the 1, 2 that seem on the low side. Okay. So my gut feeling is, just from looking at these plots, probably we're going to end up rejecting the null hypothesis that all the diets are the same and conclude the alternative that at least one of the diets is different in terms of the average length of life. You're comfortable with GMP by now that the little red triangle means I can turn things on or off. I'm going to say, oh, our method is called ANOVA. Let's just turn that one on. And you have additional input, output provided to you. Okay. Let me go down here to the very bottom first. You have means given to you for each of the groups. You have sample sizes from each of the groups. You have standard deviations, okay, such that the standard deviation divided by the root of the sample size gives you a standard error. Heck, you can even sort of say, show me the means and the standard deviations. And maybe down there, we get our mean standard deviation. And the standard deviation divided through by the root of the sample size gives us the standard error, which is reported to us with our mean/ANOVA. But our real key point here is we get this analysis of variance. The method is called analysis of variance, and it produces in R squared, sort of like what we had earlier with regression. It still has the same interpretation. The proportion of variability in lifetimes of these rats that is explained by just what they chose, what they did eat, we're able to explain like 45% of the variability overall. And our F ratio is the hypothesis test statistic. But you've learned, okay, p-value, let's focus in on p-value. That's less than 0.001. So I want to pause for a moment on that one and say, if we have a p-value less than 0.0001, that's less than the standard cutoff of 0.05, okay? 0.05 is the risk of an error of type 1 sort that I'm going to take. Yeah, literally the risk of falsely believing that the diets are maybe different if really they're all the same. So I'm saying my p-value is less than that cutoff, alpha 0.05. I believe at least one of the means is different from the others. I reject the null, believe my alternative. Okay. So any questions about getting from a p-value to a conclusion in this context? Or about the hypotheses? Okay, so what I'd like to focus on now is this hypothesis test statistic. My F ratio is my test statistic, and I want to start by saying the rest of this table reminds me of two things. One is that physics problem in high school where you did like a whole page of calculations to get a single number. And then you did another whole page of calculations in your lab book to get that second number, and a third page of calculations to get the third number. And now I'm thinking you guys were probably in high school during COVID, and so probably you didn't do lab books on paper for your physics experiments. But the point is, you have these natural places where you could say, okay, we've finished this portion of the calculations. Here is something that we need as input to the next step. Okay, that's the way I view this analysis variance table. Our friend R.A. Fisher, who invented the method, did so when he was working at home by an oil lamp or candlelight at home, after being at the Rothamsted experimentation station in the UK all day long. He would do these calculations, and he's thinking, okay, I have to get to the next whole 2 hours worth of work. Or just go to bed now. And so you circle the thing that's a natural stopping point. The natural stopping points are the things you see here. Also want to mention, this is something that's so simple my grandma could do it. Now, I only partially say that as a joke because my grandma has a degree, had when she was alive. Well, do you still have your degree even if you, well, whatever. The point is, back in 1939, not 1839, 1939, she graduated from the University of Minnesota with a degree in mathematics, where she learned all of these calculations and how to do them by hand. And when I show you the equations, you're going to say, I wouldn't want to do that by hand. And that's what I say myself. Okay. So our procedure, requires us to do these calculations and present all of them in this analysis variance table. The analogy being, well, that's the natural stop points that, you have to show people. And it frankly allows me to check your calculations more easily on a test, or it should allow you to check your own calculations more easily should your answer numerically be different from that of a friend in the class. Okay, so we like that. Another analogy that I like to use is Excel. Not that I'm a huge Excel fan, but remember when you change one number in an Excel table and all of a sudden everything else seems to change? Yeah. If you change any of the numbers in the first 2 slots in the first column, or the first 2 slots in the second column, everything else seems to be changing as well. And so just knowing our 1, 2, 3, 4 numbers here are sort of driving the rest of everything is super helpful. Okay. And then I would want to start down this path by remembering our test statistic T, and then we'll get back into our calculations here. Our test statistic T from that earlier chapter, and I'm going to give you maybe in pink the T statistic in a way that I think is super convenient for this context. If we earlier want to compare just mean 1, mu1, and mu2 with the null hypothesis that they're the same, alternative that they're differing from each other, our test statistic T was, well, X bar for group 1 minus X bar for group 2. Okay. Minus 0. Again, mathematically, that's just how I chose to phrase it. And we're going to divide through by the root of S1 squared over N1 plus S2 squared over N2. Our numerator here contains a natural way of comparing what our data are saying to what the null hypothesis suggests the data should be saying, what the data are likely to look like, if you will. If the 2 populations have identical population means, wouldn't the difference of the 2 sample means tend to be about 0 in size? The answer is yes, it would tend to be. On the other hand, if the alternative is true, the 2 sample means should be reflecting their corresponding not equal population means. That first term, the X bar 1 minus X bar 2, will tend to be non-zero. It'll tend to be positive, or it tend to be negative, depending on which is larger, the mu1 or the mu2. The rest of the hypothesis test statistic, the denominator, if you will, is capturing information about how much data do you have, the n's, and how much variability is there in each of our samples, the s's. Okay, stuff with n's and s's needs to be taken into account to allow us to use a standard T table that you guys used for the T test. The natural test statistic is just the X bar 1 minus X bar 2, but we needed to put it on the same ruler as all other ways of comparing two means. I mean, heck, if I told you the difference between mu1 and mu2 is 7 inches, you might not know whether that is large or small. But if I divide through by the standard deviations and sample sizes, the stuff with the n's and s's, we'll put it on a common scale, and you'll say, oh, that 7 difference of x bar 1 and x bar 2 converts to a t-value of 8.63. And you're thinking, well, that's really outside the negative to positive 2 range. Almost certainly that has a low p-value. We would reject the null hypothesis. So a test statistic in general is just a way of comparing what the data want to say to what, let me rephrase that. It's a way of comparing what the data do say to what the data would likely be saying if the null hypothesis were indeed true. Okay, so I'm going to sort of like get into the ANOVA space now. My null hypothesis is that mu1 equals mu2 equals all the way up through uk. And if the population means are the same, the sample means should all be quite close. And I just realized our book uses X bars rather than Y bars. So X bars are all, in some sense, close. And rather than tackling the question, what is close? How close does it need to be? I'm going after the question, how would you measure how close the X bars are to each other? I guess if I have X bar 1 compared to X bar 2, I could take a difference like we did in the t-test numerator. And then I've got X bar 1 and X bar 4. And I could, again, do a t-test. I could do a whole bunch of t-tests. But that's a lot of calculations when I only want to do one test statistic. And we're going to suggest the following. Define X bar bar as the grand mean. It's, if you will, the average of all the data points, okay? And that's literally summing I goes 1 up to k, and j goes 1 up to ni, xij over the sum I goes 1 up to k of ni. Okay, so let's give you these terms one at a time. Ni is the number of data points for group I. So if you tell me 15 data points from group 1, I know N1 is 15. Okay. Xij is value j from group I. So if I tell you the 2 subscripts, it will tell you which group you're in and which data point you are in that group. So the interior summation here is saying just add up for group I all of the data points. We're adding all the data points from that group. And then we're adding that across all the groups. And we're dividing through by the sum of the number of data points. Shoot, this is just like the average of all the data values. It is the grand mean. It's the mean of all of the data. Just a quick technical note. If your sample sizes are the same, and only if your sample sizes are the same, will this grand mean X bar bar happen to be the average of the averages. It is always a weighted average of sorts, but it is not necessarily going to be the average equal weight to every single group mean. But if all of your groups have the same sample size, then the average of the group averages is sufficient. Any questions so far? Okay, so let's get into our actual test statistic, and we'll define it piece by piece. Actually, let's just go whole hog all at once, and then I'll pull out some of the pieces. Okay. So our test statistic is the F ratio overall, okay? And the F ratio is just a summing I goes 1 up to k of and I times x bar I minus x bar bar squared. Okay. Over stuff with n's and s's. Now, so you're thinking, you're uncomfortable because you want the whole equation. I'm just saying the numerator here, okay, tells us most everything that matters. The denominator is just to put things on the same yardstick so we can make a comparison fairly. We'll give you those portions of the equation in a little bit, okay? But let's look from the inside out. First thing is we're going to compare the group mean to the grand mean. How close is each group mean to the grand mean? So let's actually even just go ahead and show you our friends here. I've got, maybe I'll turn off and on a figure. So under this display options, turn off the diamonds and add the lines. Display options, add mean lines. Okay. So we've got our grand mean shown here in gray. And how far is each group mean away from the grand mean? Well, those are just our friends right there. How far away, 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 and how far away. Some of them are very close. Others are quite far. But we're going to take the distance away from the average of all the data points and square that. Okay? And then we're going to multiply by n. So I guess if I have a group with a lot of data values, it has a greater weight overall in the F ratio. A data point or a sort of group with smaller number of data values would have fewer data points in that overall F ratio. Okay. So let me erase a couple of these things and move my graph and move on. Okay. This F ratio here is equal to what I will term, there we go, and let's go with blue. Okay. This is this numerator term I will call SS treatment, SSTR for treatment. The sums of squares between the treatment groups. Now I will just end up how do I fix it? I'm going to go with the whole on equation in sort of the way you'll be happy to see it down the road, and then we'll plug back in what it is in terms of its basics. Okay, so this is the sums of squares between the treatment groups divided by what we'll call the mean. The degrees of freedom between the treatment groups. Okay. And we're going to divide that through by the sum of squared error over degrees of freedom for error. Or I could write this as mean square between the treatment groups over mean square error. Okay. And that ultimately will be your F ratio. But let me give you the separate parts of that. And darn it, I didn't use my space super wisely. Let me maybe move this up here, and I can squeeze it in at the bottom. Hopefully this will work well. In red now, this is written as, well, summing I goes 1 up to k of ni times x bar for group I minus x bar bar squared. That's 2 bars there. Okay, we're going to divide that through by k minus 1. K minus 1 thus is what we termed degrees of freedom for error, degrees of freedom for the treatment. Okay, right there, same. Sum of squares treatment, and that numerator, the same part. Okay, so let's go back down to red here, and what do we divide through? By the sum of squares error. And I'm going to give you one of multiple equations for this. Okay, our book will present a different equation for it. This is a form that I find more convenient to use from the point of view of explaining things, or if you are given numeric summaries, you might find it very convenient to work with compared to, again, our textbook's version of the equation. Summing I goes 1 up to n, or k groups. Okay. Ni minus 1 times then s sub I squared, the standard deviation of group I. I'm going to square it, and we're going to divide that through by the sum of I goes 1 up to k, n sub I minus k. Again, some trippy equations, but let's emphasize the denominator equalities. The sum of squares error has that form, degrees of freedom error, that. Okay. Quick thought. In the same way that the numerator term, underlined here in orange now, okay, that numerator term says, how far are the data points away from the average? This denominator term says, okay, let's take the separate standard deviations in each of the groups and square them and sum them. It's a measure of spread within the groups. And I'm multiplying by n minus 1, but that scales everyone up. But if I divide through by my overall degrees of freedom for error, the denominator as a whole, okay, is termed MS error. And MS error is, interestingly enough, one of the few things that has an interpretation inside the context of this ANOVA table, this F ratio. MSE, or better yet, the square root of MS error, is like an average standard deviation. How far are data points apart from their group average? So I'm going to save this equation, or set of equations. I did a screenshot quick. Any questions before I get back into our data example and show you these guys and their interpretation in this context? Okay. So let's clear that and drag my analysis over here. Going down from the graph a little bit, we've got our friends, our degrees of freedom between the treatment groups, our sums of squares between the treatment groups. The mean square between the treatment groups is just the ratio of sums of squares divided by degrees of freedom. Mean square equals sums of squares divided by degrees of freedom. And that's true whether it's for the treatment group or for the error, because yeah, literally our sum of squared error, and let's go with a different color because that's fun to do. Sum of squared error measures how close the data points are to their group average. Okay, and divide through by degrees of freedom for error, which is just the number of data points in total, divide minus the number of groups. That gives me a mean square error, and our mean square error 40 here, 45. That's pretty close to like 49, and 49, the square root of 49 is 7. So our root mean square error says the typical data point here in this data set is about 7 units away from its group's average. Root mean square error just says, hey, how far away are you? Okay. The F ratio is the ratio of mean square treatment. F is MS treatment over MS error. And mean square treatment divided through by mean square error is going to tend to be large when the null is false. Why? Because when the null is false, sums of squares error is going to be large because it measures how far groups are, on average, away from the grand mean. If one of the groups is far above the others, it will have a larger sum of squared error. If one of the groups is a lot below the others, sum of squared error will be quite sizable. So your F ratio will tend to be big when the alternative hypothesis is true. Will tend to be small when the null hypothesis is true. How small will it tend to be? Someone always asks that question, so I might as well just go ahead and tell you. The null hypothesis will tend to be about 1 plus or minus some randomness if the null is true. If it's large enough, then you would want to reject the null hypothesis. And so let's go ahead and see how we could replicate. If I give you an F ratio, like here, I've got a 57.1043. How would you get the actual p-value? I mean, you're given it here for free, but your F distribution You need to know the numerator and denominator degrees of freedom. Numerator degrees of freedom is degrees of freedom between the treatment groups, which is 5. So I'm going to hit 5 here. And denominator degrees of freedom is degrees of freedom for error, 343, 343. Boom. And then my F ratio is like 57.1. So I'm going to sort of, I input a quantity, I get a chance out, and I'm going to get an upper tail chance, which is a p-value. So I'm going to put in the 57.1. Boom. And that says, well, shoot, this F ratio is almost entirely so down there that your p-value is tiny. So notice here, when you stretch this guy out, we're saying by luck alone, if really the diets had the same average length of life, I would tend to have something that's way the heck over here, like 5 or less. But what I got was like 57 or so, something that's so rare would happen less than 1 out of every 10,000 times. Actually, I bet you it's a lot less rare than 1 out of 10,000. But the software just rounds it 1 out of 10,000. Yeah, literally, we're saying that should be good enough for you to hit your conclusion. Let's rephrase. We would never see results like what we just saw here if, in fact, the different diets had the same average length of life in these rats. Our conclusion, the alternative hypothesis, at least one of the diets is better or worse than the others, and you might naturally want to say, which one was it? You know, clearly NP seems a little worse, but I can't say that just yet until tomorrow's class session content. Maybe N/N85 is also looking like a suspect as worse. But, you know, hey, were these two different from each other? Probably not. These two, I don't know. What about this one? Is it different from that one? I don't really know. Okay, I just lied to you. I know because I've looked at this data set before. And it will be involved in tomorrow's class session. But today, you got this lab coming up, and the lab walks you through the basics of analysis of variance, the basics of ANOVA, and, well, let's just say I'm happy. Hopefully you're happy. And after the lab, hopefully you have a better understanding than just if I shout at you over a computer screen for 50 some minutes. Good place to stop. So I'm going to stop the sharing and maybe take any questions that there are real quickly before I get going to a Senate meeting. Okay, I'm not seeing questions, and the meeting started half an hour ago, so I am saying, if you got questions, come back at office hours at 5:10. We'll see you then. Bye-bye.
For the exams, are they each going to be about approximately like 15 questions like they were for the previous exams?
They will take about the same amount of time. They will be about the same length. Some questions are maybe a little quicker than others. Yeah. And so if there's like a whole bunch of really quick questions, you know, there'll be lower points each.
Okay, sounds good. Thank you.
Take about the same amount of time. Yeah.
Okay, cool.
Mm-hmm. We'll see.